Welcome to our YouTube channel as we present once again the chemistry of inorganic elements. Today we want to present the chemistry of the first row transition element. We refer to those elements that lie between scandium and zinc to fall under the auspices of the first row transition element, referred to as the 3D transition element or the 4-period element. Intermittently, we have used transition element and D block methods. In our first discussion, we were able to differentiate between transition element and first row D block element as proposed by IUPAC. In this discussion, we will look at scandium, titanium, vanadium, chromium, and manganese as the first five, but before then, we would review their chemical properties, starting from electronic configuration. We want to start the electronic configuration of this element by showing you the argon core, which is the precursor to the electronic configuration orbital occupancy. Members of this group, the 3D element, possess the argon core, after which comes the fourth quantum state, where lies the 4s, the 3D, and the 4p. As you can see from the schematic in front of you, there is the black portion showing the argon core, which is the 288 configuration of the noble gas argon. Thereafter comes the 4s, the 3D, and the 4p, as you can see. Now, in discussing that, we take the elements one after the other. The elements one after the other start with scandium, and in scandium, you see that scandium has one electron in its 3D orbital. This qualifies scandium in the ground state to be referred to as a transition metal. But at combination state, when it combines with some other species, scandium is not qualified to be called a transition metal because it shall lose its 3 valence electrons and would not have any unpaired electron to qualify to be called transition metal. That is why on the chart you see us indicating NT, meaning that non-transition. We go down to titanium. Titanium has 2 unpaired electrons after the argon core and the 4s configuration. And there it has 2 unpaired electrons, but it forms compound in +2, +3, +4 oxidation state. In the +2 and +3 oxidation state, titanium is referred to as a transition element. But sooner than it loses its 4 valence electrons, it shall not have any unpaired electron. Therefore, you see us indicating there that it is not a transition metal. We go to vanadium, chromium, and manganese. The same applies, and you can see from the chart that at some point they are indicated to be transition, and at some point they are not transition. Furthermore, we see the chemistry of iron, cobalt, nickel, and zinc. We are particularly interested in the chemistry of nickel and copper, but we will discuss iron and cobalt. As you can see, iron has 4 unpaired electrons at the ground state, and the 4 unpaired electrons can be lost first of all by losing the 4s and the paired 2 electrons in the 3D. So iron form compounds at +2 and +3. In the +2 oxidation state, it still shows 2 unpaired electrons, and in the +3 oxidation state, it still shows unpaired electrons. So iron at any combined state is a transition, same with cobalt and nickel. But copper shows a peculiar electronic configuration of loading 1 electron into the 4s and paired electron, all the remaining 10 electrons are paired up in the 5 degenerate d orbitals. Therefore, Copper reacts and combine with other elements in +1 and +2 state. In the +1 state, copper is not considered to be a transition metal, but in +2 state, copper is considered to be a transition metal. Zinc does not show any element of transition property. We move ahead to discussing the chemistry of scandium. We see scandium to occur mostly in its +3 oxidation state, as we have stated already, when it combines with chloride, oxygen, and with such radicals as sulfate. It can be obtained from its ore through the electrolysis of scandium trichloride. Though scandium tends to be scarce, it finds its usefulness in the area of electronic devices. Scandium bears a strong semblance to the chemistry of the lanthanide because scandium is inherently diamagnetic and also shows colorless compound in its combinations. Titanium, as we know, is widely found in the Earth crust and forms about 0.6% by mass of the Earth crust. It may not be very dense or as highly dense as other transition metals. It is slightly lighter by mass, but it shows a relatively high tensile strength and resistance to oxidation, as well as high heat capacity. At this point, we say that titanium can be a very good starting material for such products that need light material but with high tensile strength, resistance to oxidation, and high heat capacity as well. The most readily available compound of titanium occurs in the +4 oxidation state, as you can see in titanium oxide, which people readily call dioxide. Titanium is found useful in the plastic industry, as synthetic fibers, and in cosmetics. We extract titanium from its ore by reacting with chlorine, where the titanium tetrachloride is further reacted with oxygen to obtain titanium oxide. Titanium is not very stable in an aqueous medium. It is gradually attacked by air to give titanium form. Titanium is unstable in aqueous medium, as we have stated, but can be found in its solid state as titanium oxide and titanium dihalide, where the halides refer to the chlorine, bromine, and so on. Notable among the halides of titanium is titanium 4 chloride. Titanium reacts readily with moisture in the atmosphere to yield titanium. Vanadium shares the same chemistry with other transition elements, except that it is slightly less electropositive than others. Vanadium reacts with the halides carbon, nitrogen, hydrogen, and oxygen to yield their respective compounds. The amphoteric compound of vanadium, vanadium V5 plus, known as vanadium pentoxide, dissolves both in alkali and acidic medium to prove its amphoteric tendency. Vanadium is mainly used in the production of special iron steel alloy with high ductility and shock resistance. It is also useful in the construction of nuclear reactors. Chromium occurs mostly in nature as chromite, known as chrome iron ore, having the chemical formula FCr2O4. Pure chromium is obtained from its ore when chromite is reduced in an electric furnace at high temperature and in the presence of carbon, according to the equation below, where you see the four red triangle indicating heat. Pure chromium has a high, bright, lustrous nature, and has high resistance to corrosion, and it forms several beautiful, interesting, colorful compounds that gives it the name chromium from the word chrome. Chromium can be found useful as sodium chromate, and sodium dichromate. They are found in the production of corrosion inhibitors, pigments, and fungicides. It is mostly used in the production of alloys as stainless steel. Manganese is a grayish-colored metal bearing semblance of iron. It is much less resistant to corrosion than chromium. Manganese becomes coated with a thin layer of its oxide upon exposure to the atmosphere. When manganese is combined with iron, aluminum, copper or zinc to obtain the resultant alloy, the resultant alloy shows a high quality or improved quality in hardness and resistance to abrasion. It is reported to exhibit the widest range of oxidation states. Manganese occurs at manganese 2, manganese 4, manganese 7, manganese 3, 5 and 6. We mentioned 2, 4 and 7 because these are the readily stable species of manganese. The 3, 5 and 6 oxidation states are not as stable as the former.